Okay, and it's a pleasure to have Brendel from University Neuchâtel, and he will talk about Lagrangian fibrations and exotic tori.
Okay, so thank you very much, and thank you for the invitation. It's my first time here in Turkey, so I'm very happy that it's such a nice place. Okay, so usually if I gave this talk in front of an audience of only symplectic geometers, I would insist kind of more on this part of the talk. But seeing as many people, I mean, the link between what I'm going to talk about today and the rest of the conference is more in the other half of the topic, I will focus a bit more on these Lagrangian torus fibrations. And so in particular, I will be interested in some sort of way of modifying a given Lagrangian torus fibration. So I will abbreviate it by LTF. And what you should have in mind, kind of, if you are aware of it, and I think many people here use, almost tori fibrations. And well, this kind of grew out of an attempt to generalize it to some situations. And in some aspects, this generalization fails, and I will maybe discuss a bit how. But in some aspects, you can do something. So in higher dimensions, for example, you can still do something. So let's say this is kind of a generalization beyond dimension 4. Of course, there are many people working on this or related topics, so I'm not claiming that this is like the one way to go or something. Far from it. Okay, so and the second part, if I have time, so I will mainly be focusing on this, and in particular, so let me give the example right away. My main example that I will be focusing on, I will give a sort of Lagrangian torus fibration of C3, fibering over. So the usual one just fibers over the positive orthant, as you may know. So the usual one would be the usual honest toric structure. It's just given by, well, I think we all know this. Let's write it down anyways. Projecting to the norm squared of the components and multiply by pi. This is normalization. And I will try to describe another Lagrangian torus fibration of these things over another basis. So this usually is just the positive orthant, so kind of the cone spanned by these vectors. But I will describe a fibration fibering over. It's almost the same, but it makes a big difference somehow over something like this. And this vector here, so let's give these coordinates some names. 0, 1, 0. This is K, 1, 1. And K can actually be any natural number. So it gives a kind of an infinite set of these vibrations. And 0, 0, 1. And okay, there are some singularities, of course, which are non-toric. This has to happen at some point. So the singularities is a ray here. I'll be more precise later on, maybe, but it's a ray here of kind of singular fibers, which are pinched tori. So on, it goes up to infinity. And here there's some monodromy hiding here. So this is between a line lying in the ZX plane and the X-axis. There's some monodromy happening there. But okay, I will go into more details. And if I have time, I will talk about the symplectic topology at the end. So I mean, you can wonder why are you interested in this. So symplectic topology, I hope I have the time. Symplectic topology, it produces exotic tori. So the fibers, there are some fibers of this vibration which are exotic. So produces exotic tori. So let me just define what I mean by this. Exotic just means tori that are not symplectomorphic to product tori. So not symplectomorphic so this is kind of my motivation to product tori. Or maybe Chekhanov published later, I don't know. And there's another paper, the one by Chekhanov Schlenk actually, that I cited before. So these two are very close to the description that I give today. So rather than the first Chekhanov paper somehow. Okay, so the Chekhanov torus is kind of, it's invariant under the circle action, a Hamiltonian S1 action, namely the one that acts like this, sort of anti-diagonal action, if you want, I don't know. And this is generated by h pi t1 squared minus this squared. And so in order to see what happens, we can do something that's called symplectic reduction with respect to this Hamiltonian. So let's do symplectic reduction, because if this Chekhanov torus is invariant, it should live in the reduced space. So let's do symplectic reduction. Have you discussed symplectic reduction at some point last week? Not so. So it just means that you take the level set of this Hamiltonian. And since it is level sets are preserved under the corresponding Hamiltonian flow, so I can divide out the corresponding group action. So this kind of thing makes sense. And under some good conditions, this is actually a manifold. And if it's a manifold, then it's automatically symplectic. So this comes with a symplectic form. With symplectic form. Omega C. So you see that this Hamiltonian is composed of components of this moment map. So the level sets of this Hamiltonian look like this. I mean, they are the pre-image of these lines or of these rays. And so I need to do actually symplectic reduction on a level set that's slightly singular. So I would like to do symplectic reduction on the pre-image of 0. But you can convince yourself that this is actually not even a smooth submanifold. But it is a smooth submanifold after you take out the origins. So let's take this out. And on this restriction, I can perform the symplectic reduction. And this turns out to be C without the origin, equipped with so the symplectic form of C, sort of restricted to this. So it's really the same as C, which is to remove the point. Okay, and So we can draw it because it's a copy of C, right? So you know what it looks like. And if I take a Clifford torus here or like a product torus here, it's also invariant under this action. So it projects to something nice, and it projects to just a regular circle here. Okay, so here there's actually a point removed. Okay, so this is removed. And I am running out of colors. Well, okay, orange. There's orange and red I already used. No, if not, it's fine. It's fine. It's fine. It's fine. It's fine. It's fine. Oh, okay, blue. Perfect. The Chekhov torus will be blue today. Okay, so one thing you can convince yourself of is that if I perturb this circle a bit, this doesn't change its Hamiltonian isotropy class because if those two things enclose the same area, then it will be Hamiltonian isotropic, and I can lift the Hamiltonian isotropy back to the ambient space. So, but if I do something slightly different, namely I put just a circle here, this is at least not obviously Hamiltonian isotropic to the one I drew. And it turns out that this is true in the lift as well. So if I take the pre-image, maybe I should be more precise. So I'm drawing circles here, but I can lift them by the reduction map to the space back to C2. So lift this to get the Chekhov torus. Okay, so this is my definition of the Chekhov torus. And you see, okay, there is a one parameter family because you can change kind of the area it contains, but this is just some sort of scaling in some sense. Okay, so what does this have to do with almost toric fibrations? Are there any questions so far?
In that case, we need to just take a circle that goes on.
Yeah. Yeah, this is a particular choice. You can, I mean, everything is up to Hamiltonian isotropy. So, yeah.
So maybe I missed this part. So there's actually for Chekhov torus.
Yeah.
That's all in this example.
In C2?
Yeah.
Yeah, this is an open question. This is an open question. I don't know. I can't tell you, unfortunately.
I ask exact one.
Sorry?
If I look for exact, are you looking for exact Lagrangian?
No. Those are not. There are no exact Lagrangians there.
Okay.
This is yeah. Monotone. Yeah. Okay. Yeah, those are monotone. Yeah. Mm-hmm. Sure. Yeah. Okay. So how does this? So let's just assume, or let's build a Lagrangian torus fibration having. So this is the second thing that I wanted to do in this example. A Lagrangian torus fibration having the Chekhov torus as fiber, having the Chekhov torus. So I will denote it by TCH for Chekhov torus as fiber. Well, and if you think a bit, so let's try to. So we have this reduced space here. No, it was blue. So let's keep the colors. This is the Chekhov torus. And now you'd like to extend it to sort of nearby Lagrangian tori. And there's an obvious thing to do, namely to just kind of extend this by circles. And Here, there's sort of, you run into kind of a problem, but let's ignore that for now. So let's just continue on with our fibration. We will see what this yields. And so on. Okay. This extends kind of Lagrangian torus fibration here on this ray here, where I did the reduction. But now I would like to extend it everywhere, so I have to go across level sets and look at the other reduced spaces. So this was the reduced space. Maybe I'll call it x0. So this is the 0 level. Yeah, minus this origin, right? And here, let's go to epsilon. There actually the level set is smooth and the action is free. So you get a smooth reduced space. There is not this problem with the origin. So let's take, for example, this version. And then I move it back to the standard one. So in 2 epsilon, for some reason, I would like to be back. This is actually also a choice, so I don't need to do it. But let's say here we are back to the standard vibration. And all of these I can lift back and get smooth tori, except for this problem here. So over this point, so I can extend kind of the smooth structure and the symplectic structure in the reduced space. But the thing that happens is that the vibration structure is different than for the other points. Over every other point, you have just a nice smooth circle. So everywhere there's circles. And here the circle collapses to a point. And the point is this origin where I had the problem. So if I lift back this circle here, it will not give me a torus, but it will give me a pinch torus. So you see the first kind of elements of the almost toric story appearing. It looks like this, and this corresponds to this point. So it gets pinched at one of the points. And if you do this kind of systematically, so I'm not saying everything one needs to say here, but if you do this systematically, you'll end up with this picture kind of that you so here there is a pinched. Here there's a pinch torus, and everywhere else you have regular fibers, and so it reproduces somehow the ATF picture, almost convergence picture. So I'm sweeping some things under the rug here. So you need to at some point really take action coordinates. So you need to think about the flux map or something along those lines, and then it will give you this kind of picture. So I took a lot of time explaining this. Okay, this is a bit vague maybe, but this is somehow convincing. And now, I would, like my goal in this talk is to do this for to do a similar story for C3. Okay. Okay, so let's see what happens for C3. So you can also do something completely analogous. You can so C3 looks like this. You can also choose the 1, 1, 1 direction here. So let's pick the 1, 1, 1 direction. And look at this set of lines here. And if you want your Hamiltonian or your moment map to have these level sets. This tells you somehow, if you choose a direction in the base, it tells you by which torus you should reduce or by which subtorus you should reduce. So we want to choose a T2 inside of T3. So here we have the standard T3 action on C3. And I choose the one, so this is in R3 somehow in the positive quotient, but in some sense this is the dual of the Lie algebra of the torus. So this is like dual of the Lie algebra. And I use this identification to tell you that there is a natural choice for this torus. Namely, there's kind of a complement, an annihilator of this direction. And I take the which will live in the Lie algebra, and then you take just the exponential of that complement. So let's say complement of 1, 1, 1. And then I will get two-dimensional. So I'm doing symplectic reduction with respect to a two torus. So I'll get two-dimensional reduced spaces. And in these two-dimensional reduced spaces, I can do the same kind of perturbation. There's just an issue, namely here you will not just have one of the reduced spaces where there will be a singularity, but actually a family living over this trivalent thing here. And if you carry out the same thing, you will get something which looks like this. So it's the upper, I don't know how to draw it. It's the upper half space, and here there's singularities. So instead of here, I just in the two-dimensional case, we pushed in one point and got one of those focus singularity, and here we have many of those. So this whole set, and here there's some monodromy. And this was kind of the first thing that I tried, but this is, you see that this doesn't resemble to the picture that I drew at the beginning. So I don't want to talk about this anymore somehow, because so here you would like to do the same kind of procedure as in the two-dimensional case and iterate this construction, but you run into a problem, which is that these singularities somehow always cross each other. So you cannot, or it's not obvious at least how to do higher mutations. So this is one thing that kind of doesn't work so well. But let me draw something else. So now I will explain to you the picture that I drew at the beginning. So this works in the first step. So there's works in the first step. But higher mutations somehow fail. Or at least I don't know how to do it. So maybe other ideas. Mutations fail. Slightly different. So let's take the same picture of C3 again. Let's fix another direction. Instead of this 1, 1, 1, I will fix a vector. I'm drawing it here for some reason. You'll see why. So it's a bit hard to draw, so I have to write coordinates. It's minus k, 1, 1. So this is the x coordinate, y coordinate, z coordinate. And I would like to do family of reductions in this direction. So if I start here at the point, let's say this is k plus 1, then I get as, and again, there's a natural choice for the torus action, namely the one that is complementary to this direction that I choose in the toric base. And if I do symplectic reduction here, I will end up also with a two-dimensional reduced space. And this point gives me an orbifold point, so I need some orbifold stuff. Looks like this. On this point here, I have the same problem essentially as there, so the action will not be free, so there will be again such a kind of distinguished point. And so if I take here, for example, the color for the toric fibers was orange. If I take a toric fiber in this reduced space, looks like this. In the reduced space, the toric fiber looks like this. And there's one other kind of candidate, if you're familiar with this story. There is one other candidate that you could try to lift, which is this circle here. So I'm trying to give it the same area, so you can imagine it maybe, yeah. It has to enclose this point and this point somehow. So I'm trying to give it the same area, so it looks a bit strange here in the drawing. But this circle here, I can try to lift. And I claim that this lifts to an exotic torus. Lifts to an exotic torus. And okay, and you can also extend it to a whole Lagrangian torus fibration by the same strategy. So you get a two-dimensional family of reductions, because you can vary where this segment lies into two independent directions, right? So maybe you want as a parametrization kind of this the point where it intersects the XY plane. So you get a two-dimensional family where you can move around this segment, and you get for every member of this family, you get a reduced space. And what happens is something similar is here. If I move it around such that it doesn't intersect this one parametric subfamily here, then this thing here, this point goes away. So, for example, this reduced space here, it will still have the orbifold point because that comes from here. But down here it will be smooth somehow. And then the two circles are Hamiltonian isotopic. This can be deformed into this, preserving areas. And so the lifted kind of tori will also be Hamiltonian isotopic. Right, okay. And this, if you go through the same kind of story as before, gives you these Lagrangian torus fibrations. And you see again, there will be some singularities, because at some point you want to include this point into the fibration. So one of the circles will have to go through it, and this produces the singular fibers. Oh. Yeah.
You could have started off with a different circle and gotten reduced with orbifold points and the distinguished points. Why were the orbifold points bad here, but okay to deal with on that side?
Yeah, that's a good question. That's a very good question. Yeah, like you would. The point is here. So here the topology was kind of less interesting. We just had a copy of C. So if you still keep the orbifold point, like maybe something interesting happens that I don't know about. But if you keep the orbifold point, there's no way of saying, like, let's say you do this family of reduced spaces, and maybe. So you may be thinking of a slope that's a bit different. So a slope like this, which would also work as long as it's rational. And then if you perturb it a bit here, in this case, you'd get an orbifold point. Okay, but then the problem is somehow that my technique for distinguishing the tori relies on the fact that if I perturb the reduced space a bit, they become Hamiltonian isotopic to product tori. And here, this is at least not obviously true, because if the circle lies outside, and you kind of keep a problem at the origin, like an orbifold point or one of these points here, you cannot say why, or you can't say why this is Hamiltonian isotopic to the standard one. I want it to disappear somehow once I perturb. And here I don't care, because so here the problem persists. I mean, there's still an orbifold point, but still the thing that I want to be true is true. Namely, I can in the orbifold point there, in the symplectic orbifold reduction, there's a Hamiltonian isotopy moving the blue one to the orange one. But I mean, this is not a real answer. This just tells you why I don't want it to happen, right? So the honest answer is I think that I don't know. Okay. And so, okay, extending the vibration means you end up with a picture like this. So actually first, it's like this, but then you can sort of put this one up, so it doesn't really matter. I will draw it here right away. So I mean, the cone spanned by these directions. So this is k minus 1, 0, 1, and 0, 0. Right. And you see, for example, so if k is equal to 1, so if the direction is this one, then it's just a standard toric base. So this comes from the fact that if I put a 1 here, actually the reduction becomes this orbifold point goes away, because the intersection will be kind of integrally transverse with the YZ plane. So actually to get exotic tori, let us fix, let's say k greater or equal to 2. And there will be the singularities, of course, which, you know, they may live so somewhere here, something like this. Kind of one parameter family of pinch tori. Right. So maybe, are there any questions?
Well, I think blue circles, do they start looking like the orange circles? Region near the orange point? Yeah,
But this is kind of a choice, right? So you can choose kind of which foliation you pick. So let's draw it again. So here's the orbifold point, and the blue one. So you start, as Umut points out. So here this is like this. So you start somewhere here, and here what happens is kind of easy. You will just get some picture like this, the circles, they will come around to the other side. So this is really just the disk somehow. And then something a bit interesting happens, because at some point you should go through this particular one here, and this will give you Well, I drew it in orange for some reason, so let's take orange. There's one orange guy which will go through. Okay, this is very bad because there the orange one was the, but okay. And then on the other side, like now you can, now that this kind of thing is freed up, so you can pull it up, and very close to the orbifold point, you can choose it to be the standard one from before. So this means, so these guys here are still product tori, the ones that are in the contained between the singularities and the z-axis. But then you can make this arbitrarily small. And I think if you admit more general singularities, you can even push it really into the z-axis, because you can sort of think of a foliation which in the limit looks somehow like this, so which approaches kind of this ray here. So where you actually never go through this point, and it just approaches a kind of ray. And so as your singularity here, if you push it all the way in, as your singularity, you will obtain something super strange. I don't even understand the topology actually. So it's the lift of this white segment to the total space.
But now,
yeah,
the other side of the interesting circle, then do you get another singularity? Do you get one of the circles pitched down to a point? Like, do you get a...
No,
you're foliating a disk by circles. So.
Oh yeah, but those are the circles living here. Those are the circles lifting to two-dimensional tori. Over, it's like in the toric case. Yes, yeah. Yeah, so here you can see that these, right, thank you, that's a good remark.
Yeah, but
they become circles.
Oh, I see. So
they become two-dimensional tori, yeah.
Where they work like in the original foliation by the orange circles, that point was the bottom point.
Yeah.
In your picture.
Yeah.
And somehow the bottom point.
Yeah.
And the other one, like the smooth one.
The smooth one. Oh yeah. Yes.
And that point moved kind of in this picture to.
Yeah.
Okay. To the right. So that blue, yes.
Yeah. So you produce these kind of pictures, and
I'm still kind of confused. Sorry, it's so in the singular fiber.
this one, yeah.
Okay, so in the singular fiber, there's that point as well, which I'm a little confused. Like, there's supposed to be the torus fixed point, and
Well, it will be somewhere here. You mean the one
for the origin, like one for the origin.
the orange one?
The orange origin.
Well, it will be this point here. Corresponds to. Oh no! Sorry. It's the one down here, where you just have a circle as a point here maps to this one in the reduced space.
So in this picture, then we have one more singularity in the singular fiber. Like maybe I'm just saying something stupid. Like there didn't used to be a point, like circles, getting smaller and smaller and becoming a point in the original location. Like here there is in the singular.
Yes. Right? Yeah. It's as before, as in the usual.
Oh.
Almost toric one. Yeah. So okay, the orange one, I never told you what these singularities are actually. They are three tori which are pinched in just one of the generators. So it's like the usual pinched tori that you are used to maybe, times this one. So there's only one of the generators.
this ray corresponds to this reduction along the x-axis.
Yeah, exactly. So yeah. There's this one parameter family of spaces. If I perturb kind of the picture, that will always have this. And this is why this is, as you point out, this is why we get a one parameter family of those. Yeah, correct. Okay, so I have some questions, and okay, maybe I'm not supposed to ask you questions, but I still have some. So first of all, how to clean this picture up somehow? How to clean this up? In the sense that this is messy, right? This is there are many things that I swept under the rug. You have to write down these circle foliations, and this is not very nice. So I would like to see kind of an algebraic version at some point of this, and I don't know how, or some kind of different formulation, because this should apply to many different contexts, right? If you take just any toric manifold, you should be able to do this at edges or at vertices. So before I did a picture at the vertex of C3, it's still there. And
so you're asking, in the first, in the two-dimensional picture, this corresponds to a nodal tray.
Yeah.
Smoothing the divisor. Yeah. What is the smoothing the divisor interpretation of what you did here? Is that?
Yeah, sort of, yeah. I just want something a bit more clean to apply to a bunch of examples and not just stay in C3 or. And then the second question is, can we iterate this? And sort of, I think in this example, the answer is yes, because nothing prevents you from doing the same kind of thing in another of the edges and kind of introducing a new bunch of singularities and moving them around. Because here there's not this problem of them always colliding somehow. And I think it should be yes, but it kind of comes back to the first question. So how do you formulate it then? I mean, it gets very messy. So it should be yes. Third point. Here, all we are doing is we fix the action of a torus of a subtorus of dimension 2 of the 3 torus acting, and we perturb in the reduced spaces with respect to this. But why fix something of dimension 2? We may even think of reducing by 1 dimension and ending up with 2-dimensional reduced spaces, and then I kind of don't know what happens, because you cannot nicely draw pictures like this and just expect any kind of smooth vibration by tori to give you something. So why keep T2 action instead of just S1? So here I really don't know what happens because this should allow you for more freedom, right? If you just fix an S1 action, you should have more freedom to perturb things kind of in the quotient. So, but you can't draw these 2-dimensional pictures, so I have no idea how it will work. Okay, so maybe if there are no questions, I would just briefly like to discuss the implications for symplectic topology. Because this is kind of the second part, which will be very short. Symplectic topology. So first of all, if I redraw this thing here, and now we think of those. So these singularities can be pushed arbitrarily close to this. So let's just assume they are very close here. And then I get kind of a family of interesting fibers, and they live over this thing here. So here I'm drawing the vector 1, 0, 1. So it lies in this plane here, formed by x and z. And all of these tori I claim are exotic. So all of these fibers are exotic. So it looks, the set looks like this. It's a kind of a two-dimensional set in some sense. And what's a bit surprising here is the fact that those are monotone. The one lying on this one-dimensional family are monotone. And the ones lying here are non-monotone. But they are still exotic and, okay, I didn't say, but they are different for a different k. So, like, let's not give them names. They and different, let's say, non-symplectomorphic. For different k. Okay, k being bigger or equal to 2.
How is k related to this 101 vector? I don't understand.
Oh, this is independent of k. So for every k, it will start there. The kind of set of exotic tori.
We went tell why is our exotic.
Oh, so why does it start there? Yeah, because the invariant that I used starts distinguishing them there. And
okay, so you don't claim that they are all possible exotic, correct?
I'm not claiming this. I actually don't know. I would suspect that those are not. And maybe
Yeah, but they're just the same, right? I mean, that's what, isn't that? Some of them just didn't change at all. Right? The ones that are close to the orbital point just didn't change, right?
Yeah, that's true. So like if my kind of singularities are here, then those didn't change. Yeah. And also, okay, so I can still say that if I move away from the plane, from the XZ plane, all of those are not exotic. You have to lie in this two-dimensional thing. But if there's a point here, so contained in the same plane, kind of, then I don't know. But away from the plane, they're not exotic. Because you see, if this point goes away, I can just deform the orange one into the blue one. There's nothing preventing me from Hamiltonian isotoping them one to the other. And this happens exactly if you move off this ray for the reductions there. Okay, so what else can I say in such brief time? Okay, maybe I didn't mention it, but this, of course, was proven by Oru at some point that there are infinitely many in C3. So sorry, I should have mentioned this at the very beginning. So this is, of course, a result by Oru. Sorry. No, this I don't know. Are they the same? I don't know. This is a completely different construction, right? So are they the same? I don't know. But he proved that there are infinitely many monotone tori in C3. And so we get, I think I get a bit more because there are non-monotone ones here included in this two parameter family. Okay, maybe sorry, 2 more minutes? Perfect. That will be enough to write down the next thing, which is kind of that now you can embed these. So this is C3, so I can, and they live very close to the origin, right? So I can embed these using Darboux charts. using Darboux charts into a tame symplectic manifold. Symplectic manifold. So this is quite a large family of symplectic manifolds. Let's say of dimension 6, but it goes higher. I mean, you can do it for of dimension. And then the theorem is that these tori will still be distinct. So still get infinitely many two-parameter families. Distinct up to symplectomorphism, distinct two-parameter families of tori. So this I was kind of surprised by that something just strong holds, but this just comes from the fact that so I didn't talk at all about the invariant that I used to distinguish them, but one can somehow just sort of sufficiently localize the invariant so that I can compute the invariant in Darboux charts. So the invariant, and it's sort of versatile deformations and displacement energy technique, can be sufficiently localized somehow. Localized. I don't have time to say what this means, okay, but I can compute it in the Darboux chart, and so it becomes somehow under some hypotheses I can compute it in the Darboux chart, and then it becomes independent of the ambient space. But I end up with kind of, there's a trade-off, so I end up with very small tori, right? Like maybe the Darboux chart is very small already, and then as I'm doing this process, I'm kind of, with every k, I'm kind of moving closer to the origin. So these tori get very small, and they are kind of like, there's no way they are monotone in the ambient space. They're very small. Yeah, so I will stop here.
Let's thank Joe. Okay, questions from the room?
How do you distinguish these, right? And how do you name it or prove it there?
Yeah, of course. I mean, I didn't talk about this at all. So it's basically the same technique as Chekhanov used in his original paper. So it's called by versatile deformations. Kind of not the versatile deformations from algebraic geometry, but it's versatile deformations for Lagrangians and displacement energy. So I can maybe explain this in, okay, I erased it, but so in the simplest example where we passed from the product tori here to these Chekhanov tori. So we are below this singularity here. So here they are Chekhanov, and here they are product. You kind of look at what the displacement energy does for nearby Lagrangians. So by this I mean here we have Lagrangian torus fibrations. So there's a nice set of nearby Lagrangians. Namely, you just perturb the small neighborhood here, and you ask what is the displacement energy of the nearby Lagrangians, and then you get a function on this space. And this actually turns out to be an invariant. So here I'm drawing the level sets of this displacement energy. And Chekhanov just noticed that although the displacement energy of this torus might be the same as displacement energy of this torus, this function behaves differently on nearby tori. And these things, so these kind of level sets here in a small neighborhood, they are invariants. So if they look different, then the corresponding tori are different. And it turns out that this invariant is extremely well adapted to doing this kind of thing, because we know the displacement energy of the product tori, and if I do small perturbations here, I end up with product tori. So if like I told you before, if I move away from this plane here, I get product tori, and I know their displacement energy. And you compute this, and it turns out that for every k, you get a different such pattern of displacement energy.
This proves exists.
Yes.
What about distinct?
Yes. So this proves that they are all distinct because it gives you a pattern that depends on k. So it gives you an angle kind of which depends on k, and then they're all different. Yeah.
So in the dimension 2 case, like 1 dimension lower, like you still use the same invariant to distinguish them, right?
Yeah.
So you have a theorem that you can apply a small neighborhood of the origin of C2 into some dimension.
Yes. Yes, this is a good question, but this is a very good question. But this invariant fails, and actually there are counterexamples where you embed your Chekhanov torus, and in the ambient space it becomes non-exotic. So no, yeah, sorry, but I mean the point is here that there are some product tori, or there are some. Maybe I should explain this later to you. I mean, so this kind of pattern actually arises for some of the product tori, and I mean product tori sitting here. So you need two things. You need this invariant plus something else to say that the Chekhanov torus is distinct. And in some spaces this fails. There are some counterexamples where the Chekhanov torus, you embed it and you expect, well, it's Chekhanov torus, so it should be exotic. But there's some global geometry of the space making it non-exotic somehow. And apparently in dimension 6, for these examples, this doesn't happen. So, yeah.
Yeah, so when you embed it in the bootstrap ambient space, how do you know the displacement energy doesn't?
Yeah, that's a good question. That's just something that Chekhanov and Felix proved at some point. So there is a theorem by Chekhanov-Schlenk. And this is another paper. This is the 15 paper. Which tells you that so you kind of embed your ball, your Darboux ball, and if you stay in a certain region, so if you take a product torus here, so what's forbidden is kind of this. So there is a set that's forbidden, which is this. And if you stay in this red set, let's say, the displacement energy of what you will embed will be the same as in the ball after the embedding. And this is what I use.
I see.
Does it make sense?
Yeah. Yeah.
So to understand this picture, you can look at CP2, and CP2 tells you that this is sharp because if you embed this ball into CP2, then you see actually that, so the kind of here the displacement would predict somehow the minimum between this component and this component, but actually it's this component here. So CP2, the embedding in CP2 tells you kind of that this is sharp because in this region it does change and there is a ball embedding. So.
And so is there some explicit relationship between this invariant and the superpotential and the monotone torus case? So presumably the way you prove lower bound of the width energy is by adding this polymer disk, whereas the sort of more traditional way to just think of something like counting polymer disk.
Sure. Yeah, I've been wondering about that myself. So if there's I mean, I don't know of an explicit relationship, but there should be some.
And I guess the more primary question would be, so for your monochrome tori, like, can you compute the superpotential? Because then you can just compare them to the Aru tori and see if they, you know, maybe
I haven't,
consider-
yeah. I haven't tried actually. I haven't tried. Yeah, I don't know. So yeah, so that's one of the obvious questions. Like, is it the same as the open Tori? I don't know.
Maybe a quick one. So for your second question, so assuming you take that, so you expect them all different, actually? With your
Yeah, somehow yes. I would expect them to be all different.
oh, so you pretty
Yeah. Yes, and there's actually some value in this because there's actually some value in carrying out this iteration because kind of if I go up higher if I take larger k, then my tori will sort of move closer and closer to the origin. So if I fix an area class, I only get finitely many. Okay, so that's kind of a weak point of this thing. When you iterate it, and I expect this to work, but I don't like this would be hard to work to write down. Because okay, the basic reason is that like this slope gets higher and higher. So if I want to stay in a certain double ball, my tori will get smaller and smaller. So actually, I should draw it differently. So let's say this is the darbu ball. Then I actually have the condition that this whole thing should be contained in the darbu ball. So if the slope gets higher and higher, I get smaller and smaller tori. So yeah, and when you iterate, then this problem should go away. So you should be able to say there's like an area class epsilon, and for this area class there are infinitely many. So okay, like this is why I wrote it like this. There are infinitely many two parameters.
Okay, another question? Any questions from the Zoom room? Okay, let's enjoy again.